right, welcome to another Fireside Chat. I'm your guest host, Megan Bergsma, and we have our CEO, Dr. Bill Cardoso, with us today. And for our guest speaker is Dr. Marcos Turqueti. Thanks for joining us, Doctor.
You're welcome.
All right, so do you want to introduce yourself and your work at LBL?
Sure. So I work here as a research engineer, okay, and I do most of my work on radiation detectors and high energy physics detectors, so these special detectors. Usually I build and design what's called front-end electronics, but I deal with the sensors too. And we go as far as going to the digital signal processing of these signals that these particles and radiation generate. So that's what I work with. And let's say our clients is like high energy physics experiments and homeland security.
Can you share with us some interesting projects you're working on right now? Of course, for public consumption.
Yeah, no, absolutely. Yeah, let's say, for example, there's two that comes to my mind right now. So one project is is to detect something that's called double beta decay. Okay, that's is an interesting thing. That's the opposite of the other project. In the sense that this project happens under a mountain in Italy. Okay, so there's a laboratory there that is located there exactly because of the low background radiation. Okay, and so this project is to try to detect these very rare events. Okay, so we have background radiation all around us, right? And this would cause false positives on the detections. So we shield everything. So we are inside this mountain, all right? It also protects against these cosmic rays that are high energy particles that comes from outer space, right? So we are inside this mountain, shielded. The project even had a shield that's very interesting. Is made with these lead bricks that come from that was used as ballast on this old Roman ships, right?
Wow.
And the reason why is because this lead has been under the ocean for thousands of years.
Wow.
Right. So the lead's not activated. It's not being bombarded by the environmental radiation, right? In the other end, we have some projects called Prism. This is for homeland security, and this, for example, it can be used for many applications. Right now, we have a prototype being used in Fukushima, right, to surveying the area. So basically, creates like it has a LiDAR that creates a three-dimensional map of the area, right? And then we have a gamma detector, a gamma array made with these CZT crystals, right, that are sensitive to gamma rays. And then so it basically do this map. It tells you where the radiation is and what elements are, right? So they are using that. One interesting thing is there's a village there that was evacuated, right? So nobody lives anymore there. And when they survey the houses, usually there's no radiation inside. But if you have if you had a leak in the roof where the water infiltrated, there is where they are seeing radiation in this abandoned house. Yeah.
So it's fascinating, right? We have in one experiment you basically are using a whole mountain as a shield.
Yeah.
Detectors. On the other one, you're looking for radiation out there, right?
That's right.
So that's something that not a lot of people know, but radiation is all around us, right? And there's radiation everywhere. You mentioned background radiation. Can you, go over what types of radiations are out there and how we see them in our daily lives?
Sure, absolutely. Well, there are many types of radiation, but I would say basically you have two general ones. One is based on electromagnetic waves, right? Basically, it's like light. Light is a kind of radiation. Just light doesn't have normal light, visible light, doesn't have enough energy to damage you, right? But as you start to increase the frequency, so for example, red is low frequency light we can see, right? As you start to increase, you go up to the blue and then violet, and then our eyes cannot see anymore, right? It's the same. Then, of course, it's still, you can still increasing this frequency, this energy. That's what we call then, for example, ultraviolet, right? And at some point, it becomes what's called ionizing radiation, right? That then it can start to damage matter by removing electrons from the shell, right? So that's one kind of radiation, right? So this goes from radio waves to light to X-rays, right? To gamma rays. And the other kind of radiation is basically atoms or their piece or parts of the atoms, right? So it's called what's called baryonic matter. So baryonic matter with high energy, that means that they are accelerated, they are at fast speeds, right? So they can be electrons, it can be protons, can be subatomic particles, but they are basically parts of atoms or atoms themselves, okay?
And how, because one of the things we, as we work with X-rays and we have samples being imaged, right, from cell phones to medical devices. Can you explain to us how that radiation interacts with the matter and how, what's the process, like the photoelectric process and all that? How do we create an image, right? Why is some radiation stopped by parts of the matter and some parts of the radiation are not stopped, right? They can go through.
Absolutely. Yeah. So let's talk about more general principles, because then again, depends a lot of what kind of object, right? And what kind of radiation, right? So let's talk, for example, an interesting thing, for example, things that can shield you from some kind of radiation can be useless for another, right? For example, that you have these neutrons, right? For example, that was found out early on with the atomic bomb, right? For example, neutrons, you can use quite successful like water and light elements to shield it, because one thing that's called cross section, right? So let's say that the neutron is like depending of its energy has a cross section, and you need these small molecules of water, right? That they are very close together, right? And then it increases the probability of interacting with neutrons. Now, lead is not that good for some kinds of neutrons, right? And you would think, oh, lead's good for shielding, right? Lead is good for shielding against electromagnetic radiation, right? So that's interesting. So let's talk a little bit more about electromagnetic radiation.
But it's all about that cross section, right? And the water, just because of the shape of those molecules, right? And the way they get together, it can stop neutrons more efficiently.
And the amount of they get much closer, right? Because of the lead, for example, is a lattice, right?
Exactly.
And they are big. They are big atoms, but they are far apart, right? So that's why then the neutrons go in between the empty space between these big atoms, let's say. and water molecules are much smaller, but they are not so far apart. So let's say the probability of interacting with these neutrons is larger.
Much larger, yeah.
So about the imaging formation, right? So to form an image with being in general using what's called the let's say shadow projection, you actually need the what you're trying to image to absorb some radiation, right? If what you're trying to image, it will not absorb the radiation, you will not see anything. It's like you're trying to image a window, right? With a visible light, it will just pass through because you're trying to project a shade, right? And if the light, for example, just go through, you'll not project anything, right? So you do need to have some absorption of the material, absorbing some of this radiation, right? And then you, it's just like a shadow, right? You have a candle, and let's say your hand, and you see the shade in behind. So it's kind of the same principle.
Mm-hmm. So you talk about radiation in your radiation environment. Is radiation bad for us, given that it's all around?
Yes, so that's a very good question, and that's there's a big debate on that. And in principle, depend. Well, we live with it, right? Certainly, we live with it. So it's impossible for you to not being exposed to radiation all the time. And there's people that there's two let's say trains of thought. One that says that you need actually a minimum exposure to radiation starts to be harmful for you. Okay, and I think that's what most of the scientists think nowadays. And there's another train of thought that say any level is bad. Okay, that's the old train. The thing is that our body is built to live with the radiation, right? So, for example, when if we didn't have a mechanism to repair ourselves when we're hit by radiation, we wouldn't live even like 6 months, okay? Because we are so our body has already mechanisms to repair DNA, right? And that's basically basically required for our complex life. Otherwise, you can't exist because then again, it's impossible. Even this mountain, right?
Yeah.
That we are still not able to shield completely. We still get radiation for the environment. Okay. So you see, we're under a mountain with a lead shield, and we still have a problem that radiation is still coming through, right? So even if you live under a mountain, you still would get some level of radiation.
Now, you mentioned this mechanism we have to repair against or repair for radiation impact. Mm-hmm. Is there a moment where this mechanism breaks and radiation becomes very harmful?
Yes, there's two situations that I would say. One is like if you have many events. Okay, so if you are exposed to a very high field that it overwhelms your body capability to repair itself, right? So that's one situation. The other situation is you can be also then again it's also is everything related to probabilities, and if you have more hits, you are exposed to a larger probability.
Sure.
And you can also have a higher energy. So higher energy is a very interesting thing. For example, both for gamma, for electromagnetic waves and for baryonic radiation, let's say, very high energy photons or neutrons, they have a very low probability of interacting with you. Okay, they will normally go through your body, and you will never know. But when they interact, they cause a lot of damage because they have a lot of energy, right? So they deposit all that energy. So that's it. Is like is these two things. So how many hits you're taking, and then what energy is this hit, right? And then you need to know that too, that as energy goes higher, the probability of interaction also reduce, right, to a certain point.
Yeah. So let's talk about something that's your specialty, right? Which is interaction of this radioactive um, particles or photons with electronics, right? And that's something we get asked a lot. Is the is an X-ray image of a component going to damage the component? And I know that's something you study quite a bit because you design electronics to go in sometimes high radiation environments, right? So how, I know there's no yes or no answer to this question, right? But give us like how you think about this process of radiation potentially damaging or not damaging electronic components.
Yeah, I would say that is interesting because it's just like our body. It's the same principles, right? It depends for, let's say, how long you're exposed. So how much of radiation is going to your body, right? Of course, different from us. Not exactly true, but electronic components, they don't have, depending on the damage, they don't have a mechanism to heal themselves, right? However, the principles are the same. If you have a lot of radiation for a long time, for example, you then depends also the energy, right, of the radiation.
Correct.
But for example, X-rays usually they will not do damage to the bulk. For example, the bulk, if you're using silicon or gallium arsenide, they don't have, usually this kind of X-rays we're talking about, they don't have energy to, let's say, damage the atoms, the lattice itself, right? They however have energy to ionize the atoms. That means take electrons away. Okay.
Correct.
And that's the way the X-rays can damage electronics. And then again, you need a lot. Usually, is a question of probabilities, right? How much photons of X-rays you're blasting to it, and then because when the X-ray, let's say, interact with the shell of electron, and let's say it happens to kick one electron out, this electron can be recaptured and nothing will happen, right? But this electron can stay on the material, what we call is like a charge trap, okay?
Right.
And that usually, if you have a lot of this accumulating, you can start degrade your electronics. It's interesting also to know that there are studies that these charge traps, they can be reversed by processes called annealing and reverse annealing, right? If you heat up the component and then cool it down, there's some probability that you can reduce this. But that I would say that's the way, this is the way that more likely that the X-ray could damage semiconductors. Okay, semiconductors. And then again, is a question of time of exposure, right? If you leave the thing a whole day there, and you have enough energy to ionize the atoms, you are increasing the probability of damage. Now, if you can manage to do something really fast, the probability will be very, very small. Okay, is everything about probabilities?
Yeah, because it has to do with the amount of power, right? Even the kV, the energy of the photon, how many photons you put in per second, how long you leave it there, and you talked to us about these two different mechanisms, right? The single event upset, which is a dynamic damage that can happen that can be fixed, right? By, for example, flipping a flop or flopping a flip that's caused by an energy deposition. And then you have what you describe, it's bulk damage, right? Where you really have a gate rupture, or you can just destroy a transistor because enough energy is deposited, right, that you can basically burn it. So how does single event upsets work?
Yeah, single events upsets, I would say it's very different. And so single events upset is something that will not damage permanently your device, right? Is basically, and they happen usually when you're operating the device, okay? And so let's say you have, let's say a transistor storing a bit, and that's saying that bit is 0. Then you have, let's say, X-ray that hits these transistors, and now deposits some energy there, and the status changed to 1. Okay, so this, and then again, this can happen even without an X-ray. Okay, the X-ray just increase the probability of happen, but you have this environmental radiation that can cause this too. Okay, but then again, this is something that you can just reset, and so this will not damage your device, right?
Yeah, so this becomes an issue if you are sending, for example, a large memory bank to space, right? There was a lot of radiation.
Yes.
And a bit might be flipped, accidentally, and that can cause, or the memory of an FPGA that might change the way the FPGA operates, right? By just changing it.
Exactly, and these, then again, there if this is a concern, there are usually techniques to avoid, like you have a triple redundancy and things like that. And so this is a big issue for huge supercomputers, because of, then again, environmental radiation. Although the probability is low, you have so many transistors in these supercomputers that you are bound to have these single events of upsets, right? Especially on these huge memory banks. So they do have ways to mitigate that, to make sure that they will not cause a big problem.
Yeah, and you can't find enough mountains, right, to put the supercomputers.
Yeah. That's right.
Now, one of the things we get asked as well is, okay, so I'm worried that my component's going to be potentially damaged by an X-ray inspection machine, but at the same time, how is that same component impacted radiated by the TSA at the airport, or the shipping company, or when it flies, right? There's so much radiation around us that the components that we receive via Amazon, right, or any other carrier, very likely have been imaged already, right?
Yeah.
And
well, this is radiation all the same, right? It's the same kind. So then again, it's a question of probability. You can have, if you're very unlucky, right, a component that will be damaged. But as you can notice, you don't see this happening, right?
No, it doesn't, exactly. Yeah.
You don't see. So you have millions of Amazon shippings, transatlantic, right? They go in airplanes. And you notice that your laptop still works, right? So that's because the probability of this happening is really small. So maybe someone very unlucky will get the computer and say, "Oh, it's not working," and maybe has something to do with this. But it could be many other things. So it's hard to say. But that just shows that the probability of happening is really, really small.
Exactly. Now, do you have what do you have to share with us about how radiation damages like plastics and rubbers and other, especially medical devices, right? And things that might be part of a more complex system. It has electronics, there's a battery, it maybe has a catheter or something that's rubberized or plastic. I mean, I don't remember seeing. Do you have any experience with that, and how radiation might damage those things?
A little bit, and plastics is they are more susceptible to neutrons, right? Because they absorb better, and gamma radiation, that is like electromagnetic radiation, high energy, right? However, there is a mechanism that you can see on plastics. For example, there's some kind of plastics that, for example, you leave outside, right? You notice that the plastic changes the color and becomes more brittle, right?
Exactly.
And that is actually a radiation damage. Usually is because the UV radiation.
UV light.
Yeah. Okay. So that I think it's called photolysis. Okay.
Exactly.
And that is basically because then again the radiation interacting with the molecules.
Yeah.
Okay. The bonds. Then it's not damage on the atoms themselves. So is on the bonds between atoms, right? And so you're creating chemical reactions there. Okay. So this photolysis does affect plastics. And so you can cause this with UV radiation, but you can also cause with X-rays. But then again, notice how long it takes for the plastics to start degrade. And it's not, and there's some plastics much more susceptible than others. Okay, there are some kinds of plastics that are really very radiation hard. So it depends on the plastic, right? And then again, depends on the time of exposure is very important. The time and intensity, basically the number of events, right?
Yeah, I just noticed that because I still have some boxes from the last time I moved. I think 20 years ago, before this last move, or 12 years ago. And the plastic on the box, the tape is brittle. So over time, and it just deteriorates, and this photolysis just makes it brittle and fragile.
Exactly.
Yeah. So Megan, how are we doing time? Last question for Marcus. So share with us what's next for you. You're working on those 2 experiments. What's exciting happening at LBL and in your career?
Well, here the lab has a lot of variety, right? So there are a lot of things. Then again, radiation is a very useful tool. Here we have called the ALS that's is being upgraded right now. It was actually used on COVID research to image the COVID virus, right?
Oh, wow.
Because exactly it produces a very pure X-ray beam, right? That is used to image the virus. So there are many things. So you never know what will be your next challenge, right? But then again, with these tools, right, for radiation, you have almost no limits, right? You have the whole medical field of people in the human body. So lots of things to do.
Yeah, we're gonna put a link to LBL on the YouTube link, because it's a fascinating lab with a fascinating history, right? From founder to the kind of work you guys do today, and more people have to learn about it. So that's it. Thanks so much for your time, Marcos.
You're very welcome. It was a pleasure.
My pleasure, man. Thanks so much. I'll talk to you soon. Bye-bye.
Bye-bye.
Bye.